Vectors, my friends, are the topic of vectors is a topic you are going to discuss quite a bit in pre-calc and in calculus, specifically Calc BC. There's a lot that has to do with vectors, and you guys will probably mostly take physics at some point if you haven't already. And there's a lot of vectors in there. We're going to connect a little bit of vectors to our triangles unit. And for part one, we are going to basically build some triangles, but define them out of vectors instead of just drawing a triangle. First of all, just to get started, a vector is a directed line segment, which means it has a magnitude, which is basically how long the segment is. And that could stand for something in the real world, like how far something has traveled or how fast it's going. Or it could be how much it's accelerating. And it also has to have a direction. That's what it means by a directed line segment. It has to have a specific way that it's pointing. So we'll have, things like 0 to 360 degrees or northwest and stuff like that to indicate which way this is pointing. So the most common example of a vector is velocity. Now, speed and velocity are close, but not the same thing. Speed is called a scalar. That's just a number. When you drive down the road and you look at the speedometer and it says you're going 68 miles per hour, that's a scalar. That has nothing to do with what direction you're going. If your car was going the other way, your speedometer would still say 68. Velocity is a vector. So it would have a number and a direction, like, for example, 68 miles per hour due east, for example. All right, so if we are in terms of a vector, we don't not only care how fast we're going, but what direction we're going. So that's the most common example of a vector, and speed is the scalar partner, I guess, of that vector. So what are problems going to look like for us? Next time we will start breaking vectors down into their x and y parts called components. For right now, we're just going to talk about how we can form some triangle problems, since that's what we've been working on, and do it in terms of vectors. So before we do that, let's talk about directions. Standard position for an angle is you start pointing east or pointing to the right, and you rotate this way. So that would be an example of about, let's say, 120 degrees. It's measured as counterclockwise from the east. Bearing, and I think different textbooks might have different versions of what exactly a bearing is. Ours is clockwise from north. So 120 degrees, a bearing of 120 would be like this. Whereas like I said, the standard position is counterclockwise from east. So depending on the wording of the problem, if it says the word bearing, then you're going to need to use this system over here where we start north and work our way clockwise versus standard position, which is shown on the left. All right, so let's get to an example. Let's use a boat. So a boat travels 50 miles east. Let's say then it turns to a bearing of, I don't know, 160 degrees. and goes 70 miles. How far and what bearing from home is just my quick way of saying how far and what bearing is it from where it was to where it is now. All right, so I didn't have this written out, so there's my quick version. So these really are not going to be much of a problem. Once you adjust to this bearing system, you're just going to be forming a triangle and then using your skills to solve that triangle and find the missing info. And that info will be found with probably the law of sines, maybe the law of cosines, just depending on what we have. So let's just draw it out. 50 miles east. So the first leg of this journey looks like this. All right. Vectors we usually draw with a segment and a little arrow to indicate which direction it was moving along that segment. Now at this point I'm going to pause and turn to a bearing of 160. So what I like to do is kind of draw in a little coordinate system so I can get my approximate direction. A bearing of 180 would be straight down. A bearing of 160 is about like this. And I'm going to go 70 miles in that direction. So that arrow should be slightly longer than the 50. I think I might not have got it quite long enough, but it's close. And my direction, my bearing, is 70. So this angle up here, excuse me, my distance was 70, my bearing is 160. And so we've made a triangle. So the question is, how long is this distance? And what bearing does that vector make? Like that. All right, so basically a lot of these problems you could use the term as the crow flies. That's just straight there, no twists and turns and change in directions. If you went straight there, how far would it be and what direction would you have to go? All right, so if you think about it, really we've got a triangle problem. We've got a side angle side situation. We're going to have to do a little math to figure out what the angle is. That's not going to be so bad. Think about this little piece right here. Would you agree that that's 20, all right, because the bearing was 160, so we were 20 degrees short of straight down, and then we've got 90 more from here, so we've got 110 degrees, okay? So, first part, how long is this red line? The red line we're going to find with the law of cosines. I'll call it x for now. X squared equals 50 squared plus 70 squared minus 2 times 50 times 70 times the cosine of 110. And I'm going to encourage you to pause the video for a moment and solve this law of cosines. And I will solve it and get right back to you. Okay, so I'm back and I've typed in the right-hand side of the equation. This is equal to x squared, my 50 squared plus 70 squared plus the rest of it. I'm going to square root that. And it's 98.96, let's call it 98.97 miles. So that's part of it. Yeah, we're in miles. And remember, though, with a vector, you don't only need to know where or how far away it is. You need to know what direction it went. All right, this has to do with a lot of real-world navigation type problems. All right, if you're trying to find something, you need to know how far away it is and in what direction. We can't just know that it's 98.97 miles. We need to know what direction it would go. Now, and we're still talking about bearings, so let me find this angle. I'll call the whole bearing theta. Theta is usually the Greek letter that we use to solve or to stand for an angle. I'm going to call this one alpha. That's a lowercase Greek, basically an A. I'm going to find that first and then use that to find theta, because I'll just add 90 to it. So now to find alpha, again, if you've got parts of a triangle, you can use whatever you want. I'm going to use the law of sines. Sine of alpha over 70 equals, let's see, what other pair do I have? I'll use sine of 110 over 98.97. All right, so I go across and across like that. And in my calculator, if I can still use that 98.97 fully accurate, I'm going to do that. So I want to go sine of 110, close parentheses, times 70, cross multiply, and I'm going to divide by the answer because that's still, that full decimal is still the answer right above. And I get 0.6646 repeating, not repeating, and going on. And then sine of alpha equals that, so inverse sine of that number will be my angle, and it's 41 point, let's just go 41.7 degrees. Now, don't forget, that's not my final answer, that's alpha. The bearing, the direction of this red resultant is, when you add two, it's called a resultant. The direction of that 98.97 is a bearing that's this theta right here. So my bearing is going to be 90 plus the 41.7, which makes 131.7 degrees. All right, so overall, the boat or whatever, I forgot what the subject was, but it's 98.97 miles away, and its bearing is 131.7 degrees. So you can exactly locate where it is with those two values. So that's going to be our first experience with vectors, just forming a triangle problem. There will be a part 2 that has some more info, but that is going to be it for now. So, Young out.